So welcome to this class. Last class we discussed, just introduced the sample preparation methods. We just discussed about the electropolishing, double layer method, and also the fine polishing, along with the use of some inert material like platinum loop. So now, but the only disadvantage with those electropolishing methods is you cannot prepare the site specific lift outs, where you need to do the field evaporation from some interfaces, grain boundaries, or some specific phases, heterophase interfaces. Okay, so now we will just go through very popular technique which is based on ion beam techniques. Ion beam techniques. Okay, so in these ion beam techniques, what we used is a focused ion beam. With this method, actually you can do the site specific lift outs. Means whatever the features you are interested, those can be lift out, those can be from those you can make needle specimens, and you can analyze by atom probe. Okay, and these methods are used for the material which cannot be polished by electropolishing. As I told you, the material should be electrically conductive. Fine. So focused ion beam can be used for those kind of materials. Okay. Usually it follows the cutting, cut away methods or lift out methods, and once these are cut away or the lift out, or the region which is interested, that is lift out, then these are sharpened until the cutout or the lift out sample becomes the sharp needle specimen. Okay, and this is done by the method called annular milling. We will come to the milling basics. Just to introduce that these are called annular milling. So we use a focused ion beam. Focused ion beam, these are nothing but a energetic ions that are focused into a fine beam. Okay, so in this slide you can see that if you have a cylindrical specimen, okay, actually you can use energetic ions such as gallium. We'll come to that why gallium is used, but just for the sake now, these gallium ions can be used by using an aperture which is called annular milling, and can be converted to a thin specimen of radius up to 100 nanometers from a cylindrical samples. Okay, so this is called annular milling. So with FIB, what we can do with FIB, these energetic ions can be used to remove material, in micron to nanometer scale from the site specific region. It means that these can be used for micro machining. What is micro machining? You can use patterning from nanometer to micrometer scale. Example, you can use for nanopores. You can generate nanopores. You can use microfluid channels, you can prepare microfluid channels, you can also make 2D to 3D structures at micron scale. Okay, and these micro machining can also be used as a fiducial markers in your sample. Okay, so here you can see that this is a secondary electron image, and you can see this is an material, and the material has been removed from this particular location, okay, around some specific site specific region where the region of interest is located here, or actually the material is removed around this site specific needle by using the high energetic ions. This is called micro machining. The second thing which can be used is the cross section. So this is your material, okay, and you can do the cross sectioning. Now if you see the top surface, this is your top surface, you cannot see the material, what is beneath, what is inside this material, okay. So actually you can remove the material so that you can actually see the cross section of that particular material, okay. So features that are hidden underneath, features that are hidden underneath the sample surface, okay. So can be these features can be explored and can be analyzed. So here you can see there is a grain boundary, okay, and you can see that by cross section you can actually see this cross section, how the crack is propagating along the grain boundary, which is not visible from the top surface, correct. So this is the cross section sample preparation. Third is the site specific sample preparation, either for TEM or either for atom probe tomography, okay. So you can actually, this is your material, you can cut the material in this particular angle, in these two particular angles, so that you can get a lamellar, and this particular lamellar, this is your side cross section. If you see in this side cross section, this is your viewing direction, and from the top, this is your top, you can see this particular lamellar which is hanging on this particular location, and it is free from this side, and you can use the manipulator to remove this particular lamellar and paste in a silicon coupon. This will come later, and you can iron polish to make a sharp needle, or you can actually thin down this particular lamellar for making a TEM sample. These can be done in a site specific sample preparation. So if you have a microstructure, if you have certain grain boundaries, actually you can locate the region of interest and you can take out the sample from that particular region so that you have you have that particular grain boundary either on the TEM sample, either on the APT sample preparation, okay. So more details we will discuss in later. First we will discuss about the instrumentation of focused ion beam, FIB machine. Fine. So we will just cover the details of FIB. I hope that you are familiar with SEM, scanning electron microscope, where you use a single column, for for imaging purpose, where it accelerates the electrons. Now coming to the instrumentation. So as I told you, a FIB is a focused beam of ions. Okay, and this particular beam on the sample surface, this is your sample, this is beam, this beam is rastered or scanned across the sample surface. Okay, and this beam is of high energetic ions. So when these high energetic ions hit to the sample, actually what you can do is, if you have a sample surface, if this high energetic beam hits to the sample, that particular sample or the material atoms, the energy is transferred from these particular ions, energetic ions. So these atoms on the surface can be removed. It is just like a trenching. It is just like a trenching in a sand. Correct? So this is called milling. Okay, so the FIB, the focused ion beam, can actually remove the material, can remove the atoms from the material, so that it trenches the region of interest. Okay, and this cut or trench or milling, so this can be told as cut, trench or milling, can be done in few nanometer scale to micrometers. This is the range of these focused ion beams. Okay, so in the construction, what are the basic things to be remembered? So you will have a electron gun or an electron gun column. Okay, you have a certain chamber. Fine. Now you have a FIB column. This is your electron gun column. This is your FIB column, and there will be a gas injection system. This is called gas injection system. Okay, and these gas injection system and FIB column are focused in such a way that it focused on the sample stage. This is your sample stage and this is your sample. Correct? And this is a complete chamber of your cross section, chamber cross section of a typical dual FIB focused ion beam and SEM machine. Okay, so the first part is electron vertical column, which is used to image, secondary electron image, backscattered electron image. The second part is the ion gun. What is ion gun? This is called ion gun. And this particular ion gun, which generates the highly energetic ions, which actually travels and hit to the sample surface. Okay. The third important part is the gas injection system, or we can call as a GIS. This is used for welding, patterning on the surface, on the sample surface. Okay, and fourth, we will describe the function of these all the parts. Okay, and the fourth is the manipulator. For in situ lift outs. So manipulator is just located here, which is a needle. This is called manipulator. Okay, and along with this you can also attach several types of other detectors that can be backscattered imaging, EBSD, then you can also EDS detectors. Okay, so these all things can be simultaneously attached to this particular chamber of FIB. Fine. So electron gun function is to generate electrons, and these electrons are accelerated across the column and hit to the sample surface, so that it generates the signals which can be used for imaging. What signals it can use? So the signals which are produced are these electrons. If you hit to the sample surface, they can produce secondary electrons from the surface of the sample and backscattered electrons, which are the incident electrons which travels across the sample and comes out. That's why these are called backscattered electrons, which gives your Z contrast. Okay, so the electron column is used for imaging purpose. What is the function of ion gun? Ion gun function is to cut, trench or milling. It means that it produces a high energetic ions. We will discuss about the gallium ions, which are very heavy. Okay, and these gallium ions accelerate across this column and hit to the sample surface, so that the region which has to be cut, trench and mill can be analyzed. Okay, so a gas injection system, it's just a particular gas. The gas, it is a chemical gas, and this gas injection system is used for welding and also the patterning on the surface. Okay, and to lift out the samples, whichever the cut or trench samples which you want lamellar, you have to use the manipulator. Okay, so we'll come to each section one by one. Okay, so first we'll describe about the ion column, which is the basic for this particular samples, for your sample preparation. Okay, so we'll describe the ion column. Okay, so this is your column. Okay, so this is your cross section of that particular ion column. Okay, which is, if schematically if I show you, this is your electron column, ion column was here, this is your gas injection system, there is a manipulator and there is a sample. Okay, so this particular column we are schematically drawing. This is your ion column, this is your electron gun. This particular column we are schematically drawing the cross section. The first is, you have a source. This source is called liquid metal ion source. Liquid metal ion source. Okay, then there will be a set of condenser lens. This is a condenser lens. Okay, then there will be a aperture with different holes, different size holes. So aperture is nothing but a plate which is having a different size of holes. Those holes, in those holes only the ion, gallium ions or the ions which are produced from the liquid metal ion source are accelerated. These are called apertures, or we can tell it as a beam selective apertures. Then there will be a set of lenses which we call as a quadrupoles. These are called quadrupoles. Which is having a hole underneath. Okay, so and there is also a pair of blanking plates. Okay, there is another set of lenses like quadrupole. There is an octopole. There is an octopole. Okay, and there is an objective lens. This is called octopole and this is called objective lens. Okay, then so this is an objective lens. So the ion source, this is called ion source. The first thing is it creates the beam. Okay, and the electrostatic lenses, as I told you, electrostatic lenses. What are the electrostatic lenses? Such as condenser lens, objective lens, all these electrostatic that controls the shape of the beam, ion beam. Okay. Third thing is beam selective aperture. Based on this aperture size, actually you can vary the ion beam size, or we can call it as a current, ion beam current. Okay, so based on the aperture size you can select you need higher current or higher beam size, or the lower beam size or the lower current based on this aperture. And the fourth thing is blanking plates. Blanking plates. So these are used in the FIB column to push the beam away whenever it is not used. Whenever it is not required. Okay, so if you have a sample here, your beam is generated in this particular source, it gets accelerated, and these condenser lenses, it means that it condenses the beam. What is the function of condenser lens? It condenses the beam. So the beam which is having a spread, it gets condensed, and by selecting this aperture you can actually select the beam current or the beam diameter, how much beam diameter has to pass through. Then it goes to this quadrupole, set of quadrupoles and the octopoles, so that they control the beam shape. They will also control the beam shape, and it goes towards the objective lens, it gets accelerated and falls on the sample surface. So whenever you don't want to mill it, so milling can be done by whether you want to do milling or not. So whenever you don't want to mill it, these blanking plates can be used to divert the beam away from the optical axis so that it will not fall on the specimen. Okay, so that is the role of blanking plates. So this is the typical reconstruction of the ion column. Now first we will discuss about the ion gun. Okay, so first we will discuss about the ion gun. As I told you, this particular ion gun is nothing but a liquid metal ion source, which is called LMIS. Okay, and most of the FIBs, focused ion beams, in the present scenario, this liquid metal source is the gallium. Okay, so this is the most common in the microscopy applications. Okay, and this instrument, by using this gallium plate, this instrument generally operate with an energy range of 500 electron volt to 30k electron volt with a beam currents of 1 picoamps to 65 nanoamps, which is a very high current. And this change of current can be done by apertures, which we have discussed just now, correct? And with this gallium ion FIB, you can get an resolution of trenching or resolution of imaging up to 5 nanometer is possible. Okay. Similarly, in the new FIBs, in the focused ion beams, they also use gas field ion system, which are called GFIS. For this, you can use helium or neon instead of gallium ions. This is the one type of source which is very common in several institutions. There is also some of the microscopes which uses gas field ion source. There is a third type of source which is called inductively coupled plasma source. Okay, and these are used. These uses the noble gas such as xenon. Okay. So based on the time for milling, you can actually use these gas filled ion sources or inductively coupled plasma sources, where the time for milling is much less, and you can actually mill the samples in a millimeter scale by the plasma FIB sources. Correct. So liquid metal ion sources, we can use the gallium ions for few microns, and the resolution is of 5 nanometers. But for the gas field and plasma sources, the resolution is much lower. So means it can be in a few hundreds of nanometers. But the rate of milling is much higher for these sources. Okay. Now, this particular class, we will just focus on the most common which is used is the liquid metal ion source. Okay, and the principle of the column and principle of the ionization is similar to the gas field and the coupled source. Okay, we will just discuss about the LMIS. Which is called gallium liquid metal ion source. Okay, if you see the cross section, we have shown that this particular liquid metal ion source, if you zoom into this source, if you see the cross section, you will have a structure like this. There is a insulating mount. Okay. There is a tungsten needle. Okay. And this is connected to a heater coil. Okay. And this particular is the reservoir. Okay, and these are the set of suppressors, we call as a suppressors. Okay, so this is a coil heater, this is your tungsten needle, this is your gallium reservoir. Okay, and from this gallium reservoir, actually the gallium metal. So gallium metal, as you know, gallium metal at room temperature, it usually is at liquid at room temperature. Okay, so this is called liquid gallium reservoir, and this gallium reservoir, the gallium flows along this particular tip and it forms a cone, sharp cone. This particular cone is called a Taylor cone, which is having a radius of 5 to 10 nanometers. Okay, and beneath the Taylor cone, you will have a extractor. This is called extractor. which is having a around minus 15 kV. It is of negative bias, correct? Because it has to accelerate the positive ions from the source. So it has a negative bias. These are called extractors. Okay, so as I told you, this particular cone, it is nothing but a cusp, a tiny cusp. Okay, and near to this tiny cusp, you will generate a very high electric field for field emission. Now I hope that you must be thinking about the atom probe. So in your atom probe needle, the needle is kept at positive voltage. There is a electrode which is kept at a negative voltage, and due to the application of DC voltage, what will happen? The atoms on the tip surface get polarized and get ionized. They will become a positive charge, and these positive charge are accelerated along these field lines towards the negative charge, negative bias, correct? This is the similar concept which is used in the focused ion beam. Okay, so here this tiny cusp which is having a very high electric field, and this is for the field emission, which is around 10 raised to power 10 volt per meter. This electric field density or electric field concentration is enough to get field evaporate the gallium, the liquid gallium, into the gallium ions, correct? So now we will talk about the gallium ions. The gallium ions. So the gallium reservoir, this is the gallium reservoir. The gallium ions are extracted from the Taylor cone. Okay, so the ions get extracted from the Taylor cone by application of an extraction extraction bias, which is a negative 15, around 15 kV. Okay, and these are accelerated down to the column. Okay, so this is your column and this is the extractor, and these gallium ions get accelerated towards the column due to the application of this negative bias. So these are accelerated down the column. So there is a field emission of gallium plus ions from the source. Okay, now we will talk about something related to the gallium reservoir. Gallium is mostly used for the so as I told you, at room temperature, so at a temperature about near to the room temperature, the gallium melting point has a 29.8 degrees Celsius. Okay, so it can be a liquid at room temperature. And gallium is a very heavy element, so it has a high mass, correct? So because of the mass density is very high, and also the gallium, the interdiffusion of gallium to the tungsten is very minimum in the liquid state. So, and the gallium is heavy enough so that it can be used for the sputtering. Sputtering means it is nothing but a removal of atoms from the surface, from the wide variety of materials. Okay. So this is the cross section of the gallium. Now we will just talk about just now we have introduced the field emission, correct? Now if you particularly see this particular needle, with the Taylor cone, correct? So I am just drawing that particular needle. Okay, and the liquid gallium will flow and it forms a Taylor cusp. So this is called Taylor cone. Okay, and this is a tungsten needle. So when you put an extractor here, which is a bias of negative voltage, what will happen? The first thing is it will induce the electric field. It will induce the electric field across this in front of the Taylor cone, which is nothing but a liquid gallium. And this electric field pulls the gallium from the needle tip. But also, due to the presence of tungsten needle and the surface, it has a certain effect of surface tension. This surface tension can put up a force against the pulling of this gallium ion towards the extractor. Okay, so once the balance is achieved between the surface tension of the gallium and also the pulling force of the bias voltage, then the liquid gallium forms a conical shape, which is called a Taylor cone, and that tip radius is between 2 to 10 nanometers or 5 to 10 nanometers. Now, due to which the electrons from the gallium atoms at the cusp can tunnel towards the tungsten tip, okay, in this particular direction. Due to this tunneling of electrons along with the tungsten tip in this particular direction, usually what will happen, this is called a field ionization of gallium atoms. Once this field ionization of the gallium atoms happens, these gallium plus ions, it gets reflected and it accelerates towards the field lines, which is called field evaporation. So here there is a combination of field ionization plus the field evaporation. This is how the gallium plus ions get accelerated towards the column, okay, due to the extractor. Fine. So so we have just gone through the cross section of the ion column. Okay, so you can see this particular region, this is an ion column, and if you see the cross section of the ion column, there is a set of lenses, there is a source, there are blanking plates, there is an aperture to control the beam current, and there are a set of lenses which are quadrupoles and octopoles which can control the beam shape and size, and also the objective lens so that it accelerates towards the sample surface. Correct? And this liquid metal ion source, the most popular used is the gallium, because it is a liquid, near to liquid at room temperature, which has a melting point of 29.8 degrees Celsius, and also it is high enough to be used for the sputtering process. And the extraction of gallium ions, it is a mixture of two basic principles, which is called field ionization and field evaporation. Field ionization, it is by the tunneling of electrons towards the tungsten tip at upwards, it makes the formation of Taylor cone of gallium plus ions, and due to the electric field and the extractor, these gallium ions gets field evaporated from the liquid and accelerates towards the column, towards the specimen surface. With this I will end this class, and the next class what we see is we will just go through other than the ion source, we just talk about the ion column and the other parts which are present in the ion column, which is related to the ion optics. Okay.